The Nexus 4 FPGA board has an onboard accelerometer that is made by Analog Devices. It's called ADXL362. If you take a look at the FPGA board and you actually flip it, you'll see that at least on my FPGA board, it is called IC number 13. This is right under the VGA in here. This is where the VGA is. This is where the SD card. So this little tiny chip is that accelerometer. So this particular accelerometer communicates with the board using the SPI protocol. So it is a low power, high resolution 3-axis MEMS accelerometer. What we get from it is actually, and what we care about is actually that it's a 3-axis MEMS, meaning it actually detects the X, the Y, and the Z. What does it actually measure? It measures a couple of things. It actually measures dynamic acceleration. It's actually from motion or shock. So if you move the board up, down, left, right, on the 3 axes X, Y, Z, it will actually detect these. In addition, it actually detects static acceleration, and static acceleration is actually due to gravity. So if it's perfectly flat, if it's on a perfectly horizontal flat surface, it should only detect the gravity of Earth, which is only on the Z direction. Actually, it's the opposite of the Z direction because Z is to the top, and it will just detect that. If it's a little bit tilted, you're going to see on the X and the Y, there's some sort of a static acceleration. Bottom line, it actually detects a static one and it detects a dynamic one. So we can actually detect movements on that board using the accelerometer. So the measurement, again, it's an analog device, but it has some sort of a digitization system inside it, and it stores it internally within some internal registers, and we can communicate with these registers by the SPI protocol. So there is actually 36 total registers accessed by the SPI, and it utilizes mode 0, and the most significant bit is usually transferred first. And if you want to configure that particular ADXL, in addition to its default values or different than its default, you can actually write to these registers and figure out how to do it, and figure out what you want to do, depending on what you want to do. You can read the manual in here. Actually, it has a very big data sheet. You can actually read it just to figure out whatever you want. However, I'm just going to go through very quickly how you actually can read and write from that particular accelerometer using SPI protocol. So a lot of devices or the SPI protocol supports full duplex, basically sending and receiving at the same time. However, a lot of devices just uses one direction at a time. It cannot just read and write. And the accelerometer, the ADXL that we're utilizing, is one of those. Even though the SPI allows full duplex, it doesn't utilize the full duplex. So it only sends or receives. So let's talk about how we can actually write into the ADXL from the processor, from the SPI, using SPI controller. And what you do is the processor, the first thing that the processor needs to do, it needs to actually lower the slave select. Basically, it's just to issue that. And lowering that slave select is extremely important for this particular ADXL because it's a control signal. And the next thing you need to do is actually you send the keyword, which is 0A. It's actually a command. You're sending a command. So, and that command is sent from the processor to the slave or to the ADXL in here. So the processor will send 0A, and the 0A indicates that you want to write to one of its internal registers. Okay, so the next word that you send after that one should be the register address that you want to write into. And then the third word, and potentially more, is the word or the byte you want to write into. Basically, what byte? And it actually has a bunch of 8-bit registers. So the registers inside it are 8-bit. So if you send only one and you end by raising the slave select, that's it. You send to that particular register address, you just basically send that particular data. Again, you issue a command that you want to write, you give it what address you want to write, and then you start basically the data you want to write. However, if you want to write to several addresses at the same time, you can give it the base address in here. You send the first word, the second word will automatically, the address will be automatically incremented so that you write it in the next register. In this way, you'll be writing in a burst mode. So basically, the processor is sending a bunch of or setting up a bunch of these 36 registers and writing into them at the same, basically at a very high speed. So if you see about it, what we were talking about is the master out, slave in. The master in, slave out is always in the high impedance because the slave, which is in this case is the ADXL, is not sending anything. So the read is somehow similar. So the first thing you need to do is actually issue the slave select in here. Okay, and then the first thing you need to do is actually you need to send the accelerometer the command 0B, and 0B indicates that you want to read from it. And the next word you need to send is what register you need to read. So basically you send the register address, and in this particular situation, because you're still communicating with that ADXL, so you're only sending to it because you're sending the command and you're sending the address, so its output, basically the slave output, is at high impedance. Next, after that second word, after you specify the register address, what you do is the processor start writing dummy data. The accelerometer is not going to take that. It's just going to ignore it. Whatever you send to the accelerometer is just going to be dummy data. If you just send one, you'll be reading one value from that particular accelerometer, which is actually the one located in that particular register. If you continue reading, for every byte you read, it's actually, this will be the base address and it will be an offset from it. And it will only end when the slave select actually gets deasserted and basically is raised to 1. And this is how you read and write from, or write and read from the accelerometer. So you need to first send a command and then the address, command and then the address. If you're writing, you write, basically you send the write signal. If you're reading, you just basically write dummy things, and you're just basically reading whatever the SPI is returning, and that would be it. So the most important registers for our purpose in terms of just reading, and the way the one we're going to be using for testing it is actually register 2, and those are basic registers internal to the ADXL. It's actually register 2, register 8, 9, and 10. So register 2 has the part ID, okay, and it's actually the part ID is F2. This is just a test that we're doing now. So what we're going to be doing is we're going to read that particular address to, and we expect to see F2. If we did see it, that means the device is operating. And then the other test, this is actually for testing purposes. This is what we do it. So it's just to make sure that everything is running correctly. And 8, 9, and 10, we can read them in a burst mode. Basically, we specify this as a burst or the base address, and then we read 3 data bytes, basically 3 8-bits or 3 bytes, and that will be the X acceleration, the Y acceleration, and the Z acceleration. The numbers you receive for each one of them will be telling you in the X-axis, the Y-axis, and the Z-axis, and the default range for this accelerometer is actually plus minus 2 Gs, and Gs is actually Earth gravitational acceleration. It's actually just in the 9.8. Okay, and the default output data rate is 100 Hertz. If you take a look at the data sheet, that tells you depending on the SPI frequency you actually set, the 100 Hertz, I think it consumes 1.8 microamps, where if you actually set it up to the 400 Hertz, it becomes 3 microamps. So you're going to be consuming a little bit more power. So depending on your application, you might need to change that particular SPI frequency. But that's as simple as it is. This is how we're going to be utilizing the ADXL. Just we have read and write operations. We're not going to change the default values. We're just going to read registers 2, 8, 9, and 10, and that's about it.